Good day, Matt E-Buddy. So today we'll be talking about the mass action law. The mass action law, for to apply the mass action law, first we need to know the charge carrier concentrations. Since the mass action law requires the knowledge of charge carrier concentrations in non-degenerate semiconductors. So for non-degenerate semiconductors, the concentration of electrons in the conduction band is equal to this one. N is equal to NC exponential EF minus EC over KPT, where NC is the effective density of states in the conduction band, EF is the Fermi energy, EC is the bottom of the conduction band, and T is the temperature of the semiconductor. Similarly, for the concentration of holes in the valence band, again in a non-degenerate semiconductor, P is equal to NV exponential EV minus EF over KBT, where NV is the valence band density of states, effective density of states, EV is the top of the valence band, EF is the Fermi energy level, and T is the temperature of the semiconductor. Also, Kb is your Boltzmann constant. So what the mass action law tells us is that for non-degenerate semiconductors, getting the product of N and P would lead to this relation. N times P will be equal to NC exponential EF minus EC over KBT and V exponential EV minus EF over KBT. If you combine the two exponentials, so let me bring up my pen, here, pen. If you combine this one, exponential EF minus EC and exponential EV minus EF, will be left, we will have, exponential of EV minus EC over KVT. Ang EV minus EC natin, this is just the negative of the band gap. So the mass action law will then state that the product of N and P will be equal to NC NV exponential of negative of the band gap over Kb temperature of your semiconductor crystal. So e.g. again, this is the band gap of the semiconductor. The mass action law is powerful since this holds true for any again non-degenerate semiconductor. A special case for the mass action law is when we're looking for the intrinsic carrier concentration Ni. Intrinsic semiconductors are those that are undoped. So we expect that N and P, or the concentration of electrons and holes at the valence band and the conduction band, will then be equal. Given this, Ni squared will then be equal to Np. Since N is equal to P is equal to Ni, again, N is equal to P is equal to Ni for the intrinsic case, and Ni squared will be equal to Nc Nv exponential of negative Eg over KBT. And we'll see here that for the mass action law, the intrinsic carrier concentration will then be a function of the effective masses of the electrons and holes, since Nc is a function, Nc here is a function of the effective mass of the electrons, and Nv is a function of the effective mass of our holes. It will also be a function, Ni of the band gap and temperature. So nakita natin dito, walang kinalaman yung doping level sa ating magiging parang mass action law. So now let's take a look at a simple example. So let's calculate the intrinsic electron concentration for undoped gallium arsenide at room temperature 300 Kelvin given the following effective masses of their electrons, the heavy holes, the light holes, and Eg, where Eg is equal to 1.424 electron volts at 300 Kelvin. So we know that the intrinsic carrier concentration Ni squared is equal to Nc Nv exponential of negative Eg over KBT. Meron na tayong value for Eg. Eg is 1.424 electron volts. Temperature is 300 Kelvin. Kb is the Boltzmann constant. Yung Nv natin, Nc natin, Nc, this is equal to 2 GD 2 pi KBT 2 pi KBT. Where is my código? Yes. ME 2 pi KBT ME over H squared raised to 3 halves Yung NV naman natin is equal to 2 pi kBT mH over h squared. Yung GD natin nito, gallium arsenide, is a direct gap semiconductor, so this will be equal to 1. Then we have mH. mH is equal to mHH plus mLH raised to 3 halves, raised to 3 halves, all over raised to 2 thirds. Simplifying, putting this expression here and here, we'll get Ni. Ni will be equal to this one. Yung mH natin is ito. And solving for this one, applying ito, we'll get that the effective or the intrinsic electron concentration for undoped gallium arsenide will be equal to 2.06 times 10 to the 12 per meter cube, or 2.06 times 10 to the 6 per cm cube. So makita natin, for an intrinsic semiconductor, mababa lang yung concentration ng electrons or concentration ng charge carriers natin in the system. And this is why, so kunyari, for a semiconductor, usually ang range nung number of atoms sa semiconductor mo is around 10 to the 22 per cm cube. Dito, makita natin yung electron concentration natin is about 2.06 times 10 to the 6. It's really low. So we can see that semiconductors, they are really poor, like, conductors of electricity at their intrinsic form. Kasi mababa lang yung concentration ng electrons, so konti lang yung kaya magdala nung ating electric charge for current or for electricity. Then they become bad conductors of electricity at their undoped form. So I'll stop here and I'll see you all in the next lecture, which will supposedly be yung ating extrinsic semiconductors or doped semiconductors. So until, well, toodaloo. Thank you.